Okay. In the second place, we need to... What happens? We need to talk about the pooling operation in the CNN. Okay. Max and average pooling. Okay. Why do we need to use that? It's used for the max pooling to feature selection. For example, if you have any data like this one, 50, 1, 2, 3. Okay. And so, what's the most active part of this data? It's the 50. Okay. And so, if you are using the 2 times 2 kernel, and so you can catch this value, and the other terms is diminished. Okay. Because this is the max part and the maximum part of these terms. Okay. And we can catch the local region pattern in here for small transition. For example, if we have this data in here, but we may also have this kind of data like this one. For example, 3, 3, 50, 49, or the 61, 1, 2, 1, and 1. And so, if you are using the max pooling layer, and then we can catch this distribution like this one. Okay? We can catch this pattern by using the what? These terms. Or we can use the average pooling in here. Average pooling means that we can calculate the whole data, and some of the data coming from the kernel is calculated and divided by the what? The number of these terms. For example, if we have the 2 times 2 kernel, and so we can collect the whole the terms and divide it by the what? The 4, and then we can get the average pooling to be assigned to the what? The new matrix. Okay. And so this is mostly utilized the robustness of your data or 2 variations. Okay. For example, if we have the what? The 50 and 50 and 4 and 1. Okay. And so if we take the data, the average data coming from this term, and so we can reduce the what? The 50 values, and so we can get the most smoothing pattern by using these terms. Or we can reduce the noise value in here. Okay. For example, if we have the data like this one, 2, 3, 7, 3, and so general pattern is here around the what? The 3 and 4 values, and so we can create the like the what? The 4 values, and so the other terms is diminished in here, and then we can reduce the minor fluctuations by using these terms. Okay, in the max pooling layer, right? Okay. So in the third place, we need to talk about the what? The fully connected layer. In general meaning, the fully connected layer represents the multi-layer perceptron or the standard neural network application. Okay. After the whole the patterns are obtained in here like this one, we can flatten the whole data into the what? The one-dimensional data. For example, 1 times n. Okay. The n is calculated what? The number of picture times length times height times width of your picture. For example, if we have the at the output of the max pooling layer, we have the 8 pictures, for example, and we have the 100 times 100 matrix, and so this n is equal to the what? 8 times 100 times 100. Okay, but it's in the form of the what? The 1D form, 1D dimension. Okay? You get it? You understand that? Okay. And then we can feed this data into the what? Any neurons, like this one. Okay? And then after that we can decide the what? 0, 1 and 0, 1 at the what? The softmax layer or the linear layer by adding these terms. Okay? This is the basic approach to what? To create your networks. Okay? Okay. So we have this information, and then I can visualize the whole this pattern in order to what? In order to show the pooling and any other layers in here, like this one. Okay? And so I can use this code like this one with the rename the word tree, the pooling. Okay? Pooling to the keras. Okay? It's the standard implementation of the R code in here, but we should set the height parameter, height of picture, like this one, 224 times 4 in the first place, and width of picture 224 times 4. Okay, this is the standard representation of the what? The R codes, which is given in the what? To changing the target size in the whole the total values. Okay, height of picture and width of picture can be assigned these terms. Okay, and so I can change the whole the code like this one, and then I can change also this code like this one, and I need to rerun this code in order to what? In order to be sure my code is right now is okay. Okay? And so my code right now is okay, but the resolution is increased, right? Because we have the greater number of data in one picture, 4 times greater, or otherwise 16 times greater in one picture. Okay, and so how can we add the max pooling layer in here? And so I can give the what? The max pooling layer 2D, because we have the 2D data in here, and so I can also give the washed average pooling 2D data at this time, right? Okay, so how can I add these terms in here like this one? The model add can be utilized in here with the parameters of the mod, the max pooling 2D. Okay, and so we should give the what? The pool size in here like this one, 4, 4. Okay, 4 times 4 matrix to be contained in the what? In this kernel. Okay, and so and at each iteration we have the 4 times 4 matrices, and then we can get the maximum values of the what? The 4 times 4 matrix in here. For example, we have in the first place the 4 times 4 matrix, and then we should search the maximum value and assign to the what? The maximum values to what? The first iteration, right? You understand that? Okay. So after that, we can run this code right now. Okay? And so this is the convolutional layer. Okay? This is the max pooling layer in the second place, right? Layer 1 is assigned to the max pooling layer, and after that we have changed the picture or the resolution or the features of this variable in here by using this term. But just remember that if we have this feature like this one, and so I can assign the 20 and 20 value in here like this one, much higher kernel can now be used in this picture. And so how can this affect the whole picture? You should see that the resolution is diminished, like this one, right? Okay, so if I choose the 40 and 40, and so this may cut the performance of your algorithm to discrete any variable in here, like this one, or any image, right? Okay, you get the difference between the higher max pooling or average pooling in here. It's good for us. Why? Decreases the resolution, right? And so in order to maximize the efficiency of your network, and so you need to select the proper number or the proper values of the watt of your max pooling. But this is highly efficient for the watt training operation, because in the last picture we have the low number values in here. 11 times 11 number is included, right? But in the second place we set the whole values 20 and 20 in here, like this one. We have the higher number values in here, right? 32, 32, okay? 32 and 32. This may be enough for your application, but maybe not. We don't know that, right? And also we can give the the average pooling layer in here, like this one. Model add the average pooling layer with the size of, for example, 2 times 2, okay? And so in the visualization or the demonstration of your implementation, we have the in the form, in the first form we have convolution, after that max pooling, after that convolution, after that average pooling. It's a bad side of the implementation of the convolutional layer. But if I choose the 2, and so if I rerun again this code, and then we will have this may be more informative for the for our algorithm. But if I change the this term 20 and 20, it's a higher values for the the average values, and so this signal must be, or this image must be more smooth than the others, right? And so we have this picture, but in this picture we have the lowest number of resolution, but each data closest to another one, right? One form is dominant in here, and also we can assign the 40 and 40 in the average pooling size. And so if we rerun this code right now, and then we will get the same tone. It's much observant, or the observable, like this one. But at the end of this code we have the only 6 times 6 data, right? And this code the converges to the 1 values, 1 common values, right? Or we select the 60 and 60, and then yes, all right. Look at the final picture. This is not informative, or this is not useful for our algorithm, and so we need to optimize the average pooling, or the max pooling, or the convolution layer, right? But the training process is highly fast with respect to the previous one, right? Okay? Yes, we can proceed with the what the any pooling there. For example, if you are saying the like this one, we can add the max and after that the average pooling. Right, this one. This. This is. Yes, you can build this model like this one. You can convert to any pre-processing fast in order to build the add operation, but in this case we will have the 3 times 3 values because this pooling size decreases the image resolution, and then we may not have the kernel size, for example 6 times 6. The output of this code generates the 3 times 3 matrix. It's highly inefficient, but if I choose the 20 and 20, and so this could be creates this higher than kernel size matrix. Okay, like this one. The output of this code is right now just like that. Okay, and so at home or you're studying this code, and then you may utilize or you may try the different codes in order to increase your classification or the regression performance. Okay, but this is this is the total history and total story about the CNN architecture. Do you understand that? Do you see that? What's the output? What's the input? And so how can affect the codes in the CNN application? You understand every part? Any question? Okay. This is the tough one because it's the easiest way to learn how the CNN works in real-time applications. Okay, and so if this is the R filter, and then we can add the for here like this one for the FCL. Okay, fully connected layer. Fully connected layer, right? Pulling 4 and 4 and 2 and 2. Okay, and so how can we add the fully connected layer? Firstly, we need to add this code to add the flatten. But in order to add the flatten, we should import the specific code like this one, the flatten. Okay, and after that we need to add the dense layer. Dense means that we can create the fully connected layer by using the dense function. Okay, dense function. So how can I add another one, the flatten add, like this one? And so we can give the model.add the dense function. For example, 64 neurons is added to the hidden layer, right? Hidden layer contains the 64 activation units, sigmoid function, for example, and or the activation can be assigned to relu function. Okay, and also we can add another layer like this one, 10, and we can give the output layer with the softmax. And so softmax means that we have the 10 output, but one of them is true, have a higher value, one value. Softmax means that. Okay, so if we have this information in here like this one, and then we can run again this code. Okay, is two-dimensional, but okay, we could change this layer like this one, but okay. If len layer activation shape is equal to plt subplot num layers 1 layer idx plus 1. This it's caused from the softmax layer, because the softmax layer is 1 times 1 matrix. Okay, it's the 1 value, and so the layer activation shape is equal to the 2, and the output is the 1 times 1 matrix, and then we should add this code in order to represent the final stage of this code. Okay, because it's just a number. Okay, so plt im show function in here, the layer activation cmap gray. Okay, and then plt title f l layer idx. Okay, this is the if condition, and the other term is the what is in the form of else. Okay, and the whole else should be added in here like this one, num channel -1 num channel idx 0. Okay, and so if I rerun this code and then bool has null in here. Okay, I'm sorry, len function cannot take a bool value because the len of the shape should be given in here. Okay, so at the final stage we have this kind of information. In the first place, we have the convolutional layer. Okay, this is the output of the convolutional layer, which is given in the what, the layer 0. After that, we apply to what, the average layer, right? Average codes result to the what, to this code, and then we add another convolutional layer, and this produces the what, the L2 layer. Okay, and after that we get the max pooling layer, and then we add the convolutional layer at the layer 4. But after that, our code creates the what, the flattened layer. Flattened layer means that this one. Okay, these pictures translate into 1D dimensional data, right? Okay, this is what, this is the directed what, the 1 point is taken in here, and place is the this one. Okay, and after that we add the dense 64 layer like this one. We have the 64 value output between the 0 to 1. Okay, and after that we add the 10 softmax layer in here, 0 to 5 minus 0 to 5. Okay, and so this is creating total 1 value in here, but one of them is assigned to the white or 1 value in the grayscale format, right? And so this is the correct representation of the what, our outcome. And so our algorithm produce this value to what, to the correct one. It's a classified one. For example, this is the orange, or the bicycle, or the pen. Okay, it's assigned to this one. This is banana, or this apple, or something like this. Any fruits can be assigned in here, but our choice is represented with what, with these terms. Okay, and so do you understand the flattened layer and the dense layer from this example, the outputs of the what these layers is showing in here. Do you get it? This values. This values means that firstly the zero value is assigned to what this matrix, the 0 and 0. Yes, and so 0 times 1 is assigned to second. For example, 40 times 40 point is assigned to this one.
100 multiplied by 100, so it's 10,000. So the first picture takes from 0 to 10,000. The second picture is the same, from 10,000 to 20,000.
Yes, but this is the 100 times 100 equals to what? 10,000. 1, 2, 3, 4. Okay? And the 4,000s. But this matrix could be this 102 and 105, I suppose. Okay? This is the size of this matrix. And then this generates to what the flattened data in here, and then we can apply the dense layer in here, and at the output we have the softmax layer, like this one. Dense layer means the multi-layer perceptron neurons. Okay? This is the hidden layer with the number of the 64 neuron. Okay? 64 neuron. Okay? Do you get it? Softmax layer. This is indicating to what the 1 value. Okay? Or the closing to 1 value. At each in the softmax layer, we will get the whole number. For example, we have 10 units and the probability of the 10 units equals to the 1. But in the highest choice is indicating with the what? With the 1 values in here. For example, in this case, we have the 0.9, for example, 90 values in here. 90% is assigned in here. Firstly, this is the whole the black. Assume that this is the 1%. Probability, this is the 2, maybe this could be is 3, or this is the 5% is assigned in the probabilistic wave on the what? On the output layer within the softmax. Okay? Do you get it? This is the total representation of the what? The CNN architecture. And so, in order to find out the best way or the best representation of your code in the CNN application, you must optimize these values. For example, we have the pre-trained networks, GoogleNet or the AlexNet in the CNN application. And so this networks is built like this one, but trained with what? In the optimized way by using the ensemble learning. In order to what? In order to separate the whole the data at each location, whatever it is. Okay? Doesn't matter. But this pre-trained networks creates the different regional patterns to catch the what? The input data to the output one. Okay? Increasing or enriching your data by using this term. And so we can use transfer learning to what? To use to pre-train data. But in the next weeks we will talk about it. Okay? But do you have any question about the CNN architecture right now? Do you get it? Okay. And so let's take a break, and then after that we have the 15 or 20 minutes to complete the whole the lesson. Okay?